Welcome to the Deep Dive. We're the show that takes sources, research, all that raw info, and distills it down so you get the core knowledge fast. Today, we're getting into something, well, it might seem a bit technical at first glance, but it really opens up how complex software gets built. We're doing a theoretical analysis of an SVG viewer application, one developed in C++.
Exactly. And this isn't just about one piece of code. It's really a fantastic window into some fundamental computer science concepts and honestly some really elegant software design.
Right, its main job is, reading and showing SVG files. But the how, that's where it gets fascinating.
That's the key. It's not just what it does, but why the design choices were made. They reveal a lot about building robust systems.
And speaking of design, this application is really modular. Each source file has a super specific job, which, makes it easier to maintain, easier to expand later on. So what can it actually do? Well, it handles the basics lines, rectangles, circles, ellipses, polygons, polylines, path, even text, all the standard SVG stuff.
And colors too, right? It's not just black and white.
Oh, yeah. It gets RGB, hex codes, even standard color names. Plus, it supports a linear and radial gradients, those smooth color transitions. And on top of that, you've got geometric transformations, zooming, panning, rotating, translating the image, all inside a Windows interface that responds to menus, keyboard shortcuts, mouse clicks, the whole interactive experience.
Quite a comprehensive example, really.
Right.
So our mission today, for you listening, is to unpack what each of these modules does, and how do they fit together, and what core computer science ideas do they actually demonstrate in practice.
Exactly. By looking at these individual pieces, you'll get insights into things like data processing, object-oriented design, rendering pipelines, event-driven programming.
All the good stuff.
Yeah, so you'll come away not just knowing what this app does, but why it's built this way, and maybe what broader lessons that offers for building any kind of complex software.
Okay, let's start right at the bottom. The absolute foundations. The base files, base.h and base.cpp. Sounds like groundwork. Absolutely the groundwork. And what's really interesting here is that these files perfectly illustrate that critical first step in pretty much any data processing pipeline. Input validation and standardization. Or sometimes people call it data preprocessing. This is where all the messy, varied input data gets cleaned up, gets put into a nice, consistent format.
Okay. So functions like trim to get rid of extra white space and remove space for commas and spaces.
Yeah.
Check for valid characters.
And things like clarify float for safely turning text into numbers, read RGB for understanding different color formats, read points for turning coordinate lists into, well, actual usable data structures like vectors of points.
It sounds like the application's utility belt almost. Lots of little tools for specific cleanup jobs.
That's a great way to think about it.
Yeah.
And base.cpp is where the actual work happens for those functions. It might look up color names in a file like rgb.txt or carefully convert those raw SVG coordinates into safer vector structures. And this immediately shows us that classic separation of interface and implementation, right?
Yeah.
Base.h declares what exists.
Promises.
Exactly, the promises.
Yeah.
And base.cpp delivers on them, hiding how it does it. All those messy processing details are encapsulated.
Which is huge for maintenance, I bet.
Oh, absolutely. Imagine if every part of the program needed to know the exact logic inside trim. If you wanted to improve trim, you'd have to check everywhere. By hiding it, you can change the implementation later without breaking everything else.
Right. So it's the cleanup crew making sure the rest of the pipeline gets good, reliable data, avoids that garbage in, garbage out problem. Makes total sense. But okay, cleaning the data is one thing. SVG files, they're XML, right? They have a structure, a hierarchy. How does the app start to understand that? I'm guessing the group files.
You got it. That brings up the next big question. How do you translate that text-based XML description into something the program can navigate internally, like an internal map? And group.h and group.cpp are smack in the middle of managing that structure, what's technically called the SVG's document object model, or DOM tree.
Okay, so group.h defines the structures, the functions for managing this tree, reading the XML, walking through the tree, handling groups, making lists of shapes. It also sets up how to store gradients and access them.
Yes, and that's data abstraction right there. You, as a user of this module, just call functions like parseSVG or getShapes. You don't need to worry about the low-level XML parsing details. Then group.cpp gets its hands dirty. It implements the actual parsing, probably using a library like RapidXML, something fast and lightweight for XML to handle the file encoding, and any syntax mistakes. It reads the main SVG tag info, the overall width, Height, the viewbox attribute.
And then it walks the tree recursively.
Exactly, recursive traversal. It goes through each node, sees if it's a line, a rect, a circle, a path, whatever, and creates the corresponding shape objects. That recursion is such a classic, powerful way to handle tree-like data.
And it has to handle G elements, the groups, especially, right? Because attributes get inherited.
Crucially, yes, it makes sure attributes from parent groups flow down to children and the transformations accumulate correctly. They don't just get overwritten. That's fundamental to how SVG works. It also digs into the def section, finds gradient definitions, stores them, maybe in a map or dictionary, so they can be reused later via xwink.href links.
So connecting this back, this module builds the internal blueprint, the program's mental model of the SVG before anything gets drawn.
Perfectly put. It's the internal representation. And, this whole process is a great example of something called the bridge pattern.
Okay.
Think of it like this. You had the XML language on one side and your internal C++ object model on the other. The group module acts as the bridge translating between them. If the XML standard changes a bit or you want to change how you represent shapes internally, you ideally only need to update this bridge module, not rewrite the entire application. It decouples the file format from the program's logic, makes it way more resilient.
Okay, cool. So data's clean, structure's understood. Now, how does it know what a line is versus a circle? How does it turn those abstract nodes from the tree into actual shapes?
Now we're getting into the object-oriented heart of it. Shapes.h and shapesreader.cpp are where this happens. Shapes.h sets up the whole class system for the geometric elements.
Right, so I'd expect an abstract base class, maybe just called shape, declaring common things all shapes must do, like draw themselves or apply transform.
Exactly. And then you have subclasses inheriting from shape. Line, rectangle, circle, ellipse, polygon, polyline, text, path. All the SVG primitives.
And these classes would hold the attributes, right? Common ones like fill color, stroke color, opacity, any transformations, but also specific ones like a radius for circle or font family for text or that list of commands for path.
Precisely. That's object-oriented modeling at its finest. You get inheritance, so common stuff is handled by the base class, and polymorphism, which means you could treat a list of different shapes uniformly, just using a pointer to the base shape class. You can just tell each shape to draw itself, and it knows how, whether it's a circle or a complex path.
Okay, so shapes.h defines the blueprints. How do they get built from the XML data? That's shapesreader.cpt.
Yep, shapesreader.cpp implements the conversion. It takes those XML nodes that group.cpp identified and turns them into concrete C++ shape objects. You'll find specific functions in there, like read line, read direct, read circle, read path, and so on.
Ah, so each read function is like a little factory. It knows exactly how to construct one type of shape from the XML attributes.
That's a perfect analogy. It's the factory method pattern. Each function is a specialist factory for one shape type. Feed it the XML data, it spits out the right C++ object, fully configured with its attributes. This keeps the main parsing logic in group.cpp cleaner. It doesn't need to know the construction details of every single shape type. It just asks the factory to make one.
And you mentioned the path element being interesting.
Yeah, because its D attribute contains that whole mini language. M for Movito, L for line boot, C for curve, A for arc, Z for close path. It's almost like a domain-specific language embedded right inside SVG, and the read path function has to parse that too.
Wow. Okay, so it's a really neat, organized system for representing every single visual element, like a factory floor for shapes. But visuals aren't just shapes and solid colors. SVGs can have those really nice, smooth gradients. How does the application handle that complexity?
Right, that brings us to gradient.cpp. And this module really highlights a key part of rendering, creating dynamic visual effects. It's responsible for processing both linear and radial gradients, which are pretty fundamental for richer graphics.
So gradient.cpp understands both types. Linear gradients use coordinates like by 1, y1, by 2, y2 to define the direction, and those can be absolute values or percentages.
Correct. And radial gradients use a center point CX, a MASI, a radius R, and optionally a focal point Phenifex XFi to define where the light comes from. The core idea involves processing the stop points defined in the SVG. Each stop has a color, maybe transparency, and an offset position. Gradient.cpp uses interpolation between these stops to figure out the color at any given point, creating that smooth transition.
Interpolation, that's basically calculating the in-between values.
Exactly. It's a cornerstone of computer graphics. You define key points, and the computer figures out all the steps in between. It's how animation looks smooth, how these gradients work. It makes discrete data feel continuous.
And I remember you mentioned xlink.href before. Does gradient.cpp handle reusing gradients defined elsewhere?
It should, yes. That allows you to define a gradient once in the def section and apply it to multiple shapes, which keeps the SVG file smaller and more maintainable.
Okay, and then ultimately it has to translate these SVG gradient definitions into something the underlying graphic system can use. You mentioned GDI Plus before, like a brush.
Precisely. GDI Plus is Windows Graphics Device Interface. A brush in GDI Plus tells the system how to fill an area. It could be a solid color, a texture, or in this case, a complex linear or radial gradient. So gradient.cpp acts as an adapter. It adapts the descriptive SVG gradient language into the specific GDI Plus linear gradient brush or path gradient brush objects needed for the actual drawing. Its data-driven design meets the adapter pattern.
It sounds like a choreographer for colors, making them blend just right. Okay, that makes sense. So we've got shapes, structure, colors, gradients, but what about manipulating the view? Zooming in, panning across, rotating the whole image. That sounds like transform.cpp's job, the math module.
It is indeed the math module. And this gets into how graphical manipulations are actually handled computationally. Transform.cpp is all about applying affine transformations. It's linear algebra in action.
Affine transformations. Okay, so transform.cpp processes all those SVG transform functions. Translate for moving, scale for resizing, rotate, and the general matrix function.
Yes. It has to parse those transform strings, which might contain multiple operations like translate 10, 10, 45. It breaks them down into individual steps and applies them in the correct sequence.
And the sequence matters, right? Rotating then translating isn't the same as translating then rotating.
Absolutely. That's the principle of composition of transformations. Matrix multiplication isn't commutative, so the order is critical. This module handles that. It deals with transformations applied to the whole view, like when the user zooms or pans the entire canvas, but also potentially transformations applied to gradients themselves, which SVG also allows.
So it's the direct link between saying transform scale to in the text file and actually doubling the size of coordinates mathematically.
Exactly. Using 3x3 transformation matrices, typically. It's the engine that allows all that dynamic resizing and repositioning.
Got it. The module with the math smarts to move everything around. Okay, deep breath. We've parsed data, built objects, handled colors, gradients, transformations. How does it all finally get drawn? How does it appear on the screen? That has to be shapesrender.cpp.
That's the final step in the pipeline. Shapesrender.cpp perfectly embodies the concept of a rendering pipeline in computer graphics. It's the module whose sole job is turning all that abstract data, the shape objects, their attributes, the transforms into visible pixels.
So it contains the actual drawing code for each shape type. What does that process look like?
Well, typically for each shape, it involves a sequence. First, save the current graphic state, like the current transformation color, etc. Then, apply any specific transformations for this shape. Next, create the right GDI Plus tools. A pen for the outline, stroke, and a brush for the fill. This is where the gradient brushes from gradient.cpp would be used if needed. Then, tell GDI Plus to fill the shape's area using the brush. After that, tell it to draw the shape's outline using the pen. And finally, crucially, restore the graphic state back to how it was before drawing this shape so it doesn't affect the next one.
That sounds meticulous. And for things like text, it has to handle fonts, alignment, maybe character encoding like UTF-8.
Oh, yes. Font rendering is complex. And for paths, it has to interpret those MLCQAZ commands again, but this time to actually draw the lines and curves, keeping track of the current point as it goes.
Yeah.
This module really shows a fine geometry being applied again during rendering. It shows how complex curves like Bezier curves, CQ, and arcs A are actually drawn, and it highlights that clear separation between the data model, the shape objects, and the final visualization on screen.
This is really where the magic happens, isn't it? Where all that setup pays off in a visible image you can interact with. Amazing. Okay, we've toured all these specialized modules, the cleaner, the architect, the factory, the color choreographer, the mathematician, the artist. But something has to run the show, right? What brings them all together and makes it a working application? I assume that's main.cpp.
Absolutely. If we think about patterns, main.cpp is acting like the controller in an MVC-style architecture model view controller. The shapes are the model, the rendering is the view, and main.cpp is the controller connecting them and handling user input. It's the hub of what we call an event-driven program. The application isn't just running top to bottom, it's reacting to things happening, user clicks, key presses, window resizes.
So main.cpp pulls everything together into an actual Windows application. It handles starting things up, initializing GDI plus dower, getting the SVG file path from the user, telling group.cpp to parse it.
And it creates the main window, the menus, file view, etc.
And then it sits and waits for events. Like if the user selects zoom in from the menu, or presses a keyboard shortcut for panning, or drags the mouse.
Exactly. It manages that event loop. It catches those user actions, figures out what transformation is needed, updating data managed perhaps by transform.cpp, and then triggers a redraw. When Windows sends the WMP AND message telling the app, hey, you need to redraw your window, main.cpp orchestrates the rendering process, telling shapesRender.cpp to draw all the shapes, applying the current view transformations.
And clean up too, when the user closes the app.
Crucial. It's responsible for freeing all the memory allocated for shapes and other data structures and properly shutting down GDI plus CB. Good resource management is vital.
So it really is the brain, the central nervous system, making the whole thing interactive and functional for the user.
Wow. It's quite something to see how these distinct parts create the whole experience. So, wrapping up this deep dive, it's pretty clear that something seemingly straightforward, just displaying an SVG file, actually involves this whole symphony of computer science principles working together. It's definitely not just opening a file.
Not at all.
Yeah.
This theoretical SVG viewer is a beautiful illustration of so many core concepts. Modular design, hiding complexity through abstraction and encapsulation, the power of object-oriented programming with inheritance and polymorphism. We saw specific design patterns like factory and adapter, the application of mathematical foundations like affine geometry, the responsiveness of event-driven programming, and the importance of responsible system management, like handling resources properly.
And what this really drives home, I think, is that these aren't just dry academic ideas from a textbook. They're practical, effective solutions to the real challenges you face when building complex software. They make it possible to build something robust and adaptable. So here's a thought for you to take away. Next time you're using an application, maybe zooming on a map on your phone, using a design tool, even just browsing the web, think about the complexity likely hidden beneath that simple interface. Can you start to sense those layers? The data being processed, the internal models being built, the rendering pipeline turning data into visuals. Even though you can't see the code, you can start to appreciate the underlying architecture.
And maybe a final thought. Understanding these ideas, breaking problems down into manageable, interconnected, specialized parts, isn't just for software folks. It's actually a powerful way to think about tackling any complex challenge, building something strong and flexible piece by piece.